I think what I'm going to do is I'm actually going to record this also. So I don't know how well the stream is going to keep up because it seems like it keeps buffering, but I'm going to record it so that I can just post the video of the recorded thing. Hopefully the stream can keep up, but it's acting like it buffers pretty often, so that may not be very enjoyable to watch. So I'll just record it also, and I'll post that recorded video. All right, so torsional shear stress. What I'm going to do is I'm going to take a cylinder. So you could apply torsional forces or torques to any particular shape, but in engineering, a lot of times the shapes that are needing to deliver torque are cylinders. They might be tubes, so they might be hollow, or they might be rods in solid cylinders. But they're normally, I guess, maybe not normally, but the most common things are going to be that shape. You could have hexagonal members that are delivering torque, or rectangular, or prismatic of some shape, but most of the time it's going to be a cylinder. So that's what we're going to focus on, and that does limit one piece of our equation. Like this equation that we're going to derive here is not completely transferable to just any cross-sectional shape, because, and you'll see there are parts of it that rely on this thing being a circle. Oh, and there went the there went the stream. I just don't know what the deal with the internet is, and I don't know if it's the internet or if it's something else going on. But here we've got, let me go over here to OneNote so you can see what we're looking at. Here we've got kind of a 3D-ish view of a cylinder. I'm going to try and put a little circle on the end of it. Didn't quite line up, but that's okay. We'll kind of cheat a little. There we go. Now it looks good. Let's go ahead and make this hollow so that we can add in a couple of our variable names. So we'll make it hollow. All right, so I've got this pipe or this tube, and what I've got on it is some kind of torque, and I've got an opposing torque. So there's going to be one maybe like this, and then I've got some dimensions. Right now we don't need this one yet. We will, but we're going to label this as just L for length, so however long the pipe is, or the rod or shaft or whatever it is, we'll just call that L. I'm going to call and this is, I might have to zoom in. Yeah, there we go. I'm going to call this dimension here, I'm going to call that B. So that'll be the inner radius. And then I'm going to call C the outer radius. And these are radius, not diameter numbers. So C would be out to here. And then for the purpose of setting up our equation, it might be that you don't want to know the stress at B or the stress at C. You want to know the stress somewhere between those or somewhere else. So I'm going to put another variable in here just at some arbitrary radius, and that's going to be rho. Like that. Okay. What else do we need? We've got our torque that's causing, this is going to create a shear stress, right? So the shear stress, I guess I can write this down. The tau will be the shear stress. Torsional shear stress, or shear stress due to torsion or torque. And it will be 0 at the center at radius equals 0. And it will be maximum on the outer surface of this pipe or cylinder or whatever it is. Okay, and it will vary linearly between those 2 points. So that we're going to assume that it's 0 at the center, the torsional shear stress 0 at the center, maximum on the surface, and it varies linearly between the 2 points. All right, I think that sets us up with all of the variables that we will currently. There's one more. I don't think I want to talk about it yet, though. It's going to be called the angle of twist. So when you're applying a torque to some shaft, it might rotate. So it might spin and deliver some power somewhere. But it might also, at the same time, even as it's rotating, it might twist, and we can calculate that amount of twist too. So like a spring could actually do that and store energy, or a shaft could do that and just kind of twist, and maybe it twists too far or whatever. We'll deal with that separately. So I don't want to clutter up our diagram with that. We don't need it just yet. We'll get to that maybe tomorrow. I did notice that it looks like the stream just decided to completely shut down. So I don't know what to do with that. I'll have to see what is actually going on there, but we can just watch this delayed. All right. So we already know, based on we're working off of this diagram with basically just T, rho, and then this idea of inner radius and outer radius. It is possible the inner radius B is 0, so it's a solid shaft. That is, I just keep it in there as a variable because it's not necessarily true that it's always a solid shaft. It could be hollow. Then we have, let's see what that was. Yeah, hold on a second. Let me post to Discord that the stream just shut down, because if you were watching it, you can't hear me right now. So I'll do that real quick, assuming I can get there real quick and let y'all know. So what we're going to do here, and while I'm doing this, is we're going to take the idea that stress equals force over area. So that was kind of our definition of average stress anyway. And we're going to take that, and from that idea, we're going to derive an equation for torsional shear stress. Here, I'm going to post to Discord here. All right. Let's see, where did my pen go? There it is. All right, so the idea, stress equals force spread out over some area. That's the same idea we started with on like the first day when we did axial stress, because that's just the definition of what stress means, is that you've got some kind of force. In this case, it's a torque, but some kind of motivating factor here that's a force, and it is spread over some area. And the larger the area, the less stress. The smaller the area, the more stress. All right, so we know this, and we could rearrange this to say stress times area equals force. So that's just the same equation, but solved for force. Okay. We also know that in this case, we're dealing with torques. And so torques aren't quite forces. They are a force that's applied at some distance. So a torque, or a moment, is a force times a distance somewhere. That's creating that twisting effect. And for us, you know, we do make a distinction between the idea of a moment and a torque. This is the case where we normally talk about them as torques. So a torque is usually applied to a shaft, and it's trying to make the shaft twist or spin. A moment is trying, you know, they are exactly the same thing. And if you're looking in a physics textbook or whatever, they probably don't even bother with two separate ideas. But we just use it more as a nomenclature, like semantics type of thing. But we do have this idea that a torque, equals a force times a distance. Okay, and now I've got two definitions that include force, right? So I'm going to sub in, and I've got torque. Whoops, let's write it in the same color though. I've got torque equals force is equal to stress times area. And then times distance. So all I did is substitute in a different definition for force here, the stress times area definition. All right, let's write this instead of words. Let's write our variables. So torque, and I'm going to take, and let's go back here for a moment, and let's put another shape in here, and it's going to be maybe right there, but well, let's make it a little more. That looks okay. Let's say that we'll put, this is kind of a dotted line. Okay, little dotted line there, and that let's reline this up here. Oh, oops, didn't want to erase it. Let's just put our row variable on that dotted line. I'll make it a little smaller. So row can be any radius I want it to be in the shaft. So I'm going to say that it's the one that's landed on this dotted line. And then I can take a delta row, right? So I could have another little dotted line out here, and I could have, let's write it in blue, D row. So it's just like making the little integral rectangles where they have a dx width and some height going up to a function. Same exact thing here, except my rectangles are now rings. All right, so I could have, looking at my word equation here, I could say that I've got a dt, so some torque on one of those little rings, equal to stress is this torsional shear stress, tau. I will say that it's tau rho, so it's the torsional shear stress at that position rho. That is, it could be anything. It could be equal to B or C or anything in between. Times the, let's go ahead and do that's stress. So torque is there, stress is there. Let's actually put distance next. So distance is going to be here. The distance is measured from the center outwards. That's rho. And then the area we'll put over here. That's going to be, I'm talking about a little differential ring. So this is a differential area, dA. So I've got this little equation now. Now what I want to do, so this is kind of a generic equation that I could establish for calculating the torque on any particular surface, or if I, not surface necessarily, but any slice ring shape of the cylinder. Or I could take and use that same definition to calculate the stress on that slice of the cylinder. One other thing I want to do though here is I'm not normally interested in that. A lot of times I want to know the maximum stress. Tau at C, the maximum stress is at the surface where the radius is C. So tau C. And I do know that tau rho, that's supposed to be a rho, not P, tau rho equals the ratio of rho to C times that maximum stress on the surface. So because one of the earlier things I said when we were looking at this picture was that the shear stress is 0 at the very center of the shaft, and it's maximum on the surface, and it varies linearly between those 2 points. And so that's what this equation is basically saying, is that there's a linear relationship between the stress at some point and the maximum stress on the surface. Okay, so taking that idea, I can plug this guy in there, because they both equal tau at some random point rho. So then my equation says, all right, dt equals rho over c times that maximum stress on the surface times rho times dA. So now I've got this differential set up here, and I can integrate both sides. So integrate dt equals integrate rho over c d c or tau c times rho dA. Integrate that side. So the integral of dt is just t, so the torque. This other side has the variable in here is rho. You know, it's the thing that can vary from rho equals 0, the very center of the shaft, to rho equals c, the outer radius of the shaft. So it can vary in between those two extremes. Tau c is a maximum shear stress. It does not vary. It is just the maximum. C is the outer radius, so that doesn't vary. That's just the outer radius. Now, I guess you could have some like a tapered shaft where the outer radius does vary, and we could use this equation directly to do that. But we're going to take and solve this equation for the general case of the shaft just being a uniform tube or a uniform rod. That's circular cross section. We are assuming they're a circular cross section. Actually, I guess we're not quite assuming that yet, but we're about to. All right, so T equals, let's take out our constants, tau over C, or tau C over C, integral rho squared dA. That integral rho squared dA looks a lot like integral of y squared dA, where we had the second moment of an area type of thing when we're doing moment of inertia. Let's change it a little bit though, and let's look at what this dA looks like. I guess we're not going to change it, we're just going to add on to it. Is that a circle? Add another one. Let's make it a little more circular, or at least concentric. That looks fine. So there's our little d rho thick ring. And the current inner radius is rho. You know, so this isn't necessarily the profile of the whole tube or anything. It is just a differential ring that exists in however thick the tube is or the shaft is. This shaded area, if I were to try and color it in, that area is dA. So taking that, dA must equal 2 pi rho, so that's the inner perimeter, times d rho, however thick that ring is. And now I can take this definition, that's what dA actually equals, and plug it in for dA, right there. So now, and this is where we make the assumption that we're only talking about circular shafts, because we just defined the area to be a circular ring. If it was a rectangle, then this area would be different. So this is where the equation becomes specific to circles. It could still be a hollow circle, but it has to be circular. All right, so let's see, now we have T equals tau C, maximum shear stress, over C times integral of rho squared, and now dA is 2 pi rho d rho. So we have some more constants and some more rhos. So T equals maximum shear stress, torsional shear stress, over C, outer radius, 2 pi, those are constants, and then integral rho cubed d rho. Okay, now we can go ahead and integrate the rho cubed d rho. So T equals maximum shear stress over outer radius 2 pi. Integral of rho cubed d rho is rho to the fourth over 4. And then we will evaluate this thing from whatever our inner radius is, which way back up here, we said our inner radius was b on this picture right here. So from whatever the inner radius is, which could be 0, all the way out to the outer radius, which we labeled c. So those are going to be the limits on our little integration here from b to c. And we will have T equals tau c over c times 2 pi, and then rho to the fourth over 4, we're going to plug in c, so c to the fourth over 4, and then we'll plug in minus b to the fourth over 4. So we're just plugging in c and b for the rho, the variable. And now we've got our equation. Now, normally we're not solving for torque, though. Normally we're solving for shear stress, when we're given a torque, or we know the torque. So we are going to rearrange this to solve for tau sub c, because that's what we normally want to know is the maximum shear stress. So that equals T, the torque applied to the cross section we're talking about, times c, the outer radius. Again, that's for the maximum shear stress, over let's see, I've got some pi, or I had 2 pi, now I've got pi over 2. Let's see, oh yeah, because I had c to the fourth over 4. So I'm going to take the 4s and the 2s and turn that into pi over 2 times c to the fourth minus b to the fourth. There are some versions of this equation that use the outer and inner diameters here. And then they have what, like pi over 32 is what that would be, I guess. Or we could just have tau rho. So maybe we don't, for whatever reason, want to calculate the shear stress on the surface where the maximum shear stress is. There might be some reason you want to know the shear stress on the inner surface or any other point. So tau rho would be that equation. The only difference would be T times, you just plug in whatever rho equals. And then pi over 2 c to the fourth minus b to the fourth. A lot of times, though, you see this equation written as tau c, if we're doing the maximum one, tau c, t times c over j. So j is like I, where I was the moment of inertia for some prismatic shape. J is the polar moment of inertia. And it only works for the circles because of, we put in this definition for dA earlier that's based on a circle. And it just equals pi over 2 times c to the fourth minus b to the fourth. And a lot of times b, the internal radius, is 0 for a solid shaft, so it's just pi over 2 times c to the fourth. All right, so that is going to be our derivation of the shear stress equation for a shaft in torsional stress. So that's it, TC over J, or T rho over J, whichever might apply to the situation. So let's see how that would work. Let's do a simple one just to make sure we're knowing what all the variables are doing for us. And then maybe we'll grab some web work problems. So here's a little shaft that's attached to some stationary object like a wall. We'll make this a solid shaft. we'll put a torque on it of 50 foot-pounds. And that 50 foot-pounds, that's the external torque. The torque in this equation is an internal torque, so I do have to make sure that I'm cutting the free body diagram open so that I can see what's going on inside it. In this case, it's pretty obvious, but it does get more complicated when there's more things going on. So there I'm cutting it apart, and I'm going to put the external 50 foot-pounds. And for this little piece to be in equilibrium, I have to be able to balance that 50 foot-pounds with 50 foot-pounds going the other way. So that internal one is the one that actually goes in the equation. So if I want to find the maximum shear strength, well, I have to have a diameter for this thing, don't I? Let's say that the outer diameter of this shaft is 3/4 of an inch. Can y'all see that? That's really thin. Let me make that bigger. There we go, 3/4 of an inch outer diameter. So tau max equals T times C over J. T, the internal torque, is 50 foot-pounds. C, the outer radius, is half of the outer diameter, so 0.75 inches over 2. I've got a mismatch in my units in the numerator. I've got feet times inches, so let's convert the feet over to inches because I want pounds per square inch in the end, so might as well get rid of the feet. So 12 inches per foot to cancel the feet in Greek inches. And then J, this one is a solid shaft, so it's just pi over 2 times the outer radius, which is the 0.75 inches over 2. That number raised to the 4th over 4. I've been writing it in parentheses, but that was because we had minus b to the 4th, but right here. Oh, I don't need, I already took care of the over 4, so I just need minus c to the 4th. Let's get let's get math. I think I have MathCAD open because I don't have a calculator handy right here. And let's see if we can put these into a equation to solve for. All right, so we had B was 0.75 inches. We had T was 50 foot-pounds. MathCAD will want pound force for that. We don't have a value for J. We'll calculate that one here in a sec. Well, actually, I guess we can do it this way. J equals pi over 2 times C to the 4th, which we don't, I wrote B equals, B does not equal that. OD equals that. Sorry about that. And then let's go ahead and put C is half of, OD is outer diameter. There we go. And let's write our equation for tau. So tau max is equal to T times C over J. And we want PSI or KSI. So it looks like 7,243 pounds per square inch. And then we could take that number and let's see if I've got a material property chart pulled up somewhere. I can get one. Here comes one. So here we've got our material properties. Let's zoom in. These are the right units, and we didn't define a material. Let's just say it's that structural steel. So right here, this 36 KSI, that's the tensile strength. Now this is a shear stress, so we have to compare that to a shear strength. Remember, if we go, I didn't really, guess I pointed that out, but if we look at this here, the way the torques are applied, they are parallel to the surface that we calculated this area from, right? The torque is parallel to that. So that creates a shear stress instead of some kind of axial stress. So this number, oh, I guess I could write it down. This number equaled 7,000, I forgot the number, 243 psi of shear stress. So we compare that with a shear strength, which is not listed for the structural steel. So when they're not listed in a material property chart like this, that means there are multiple ways that you might estimate the shear strength based on the tensile strength. We're going to take maximum shear and just say that for a really conservative and simple approximation of the shear strength, just take half of the tensile strength. There are more accurate models, distortion energy, things like that, that you can use to get a more or a less conservative but more accurate estimate for the shear strength. And you will do that in other courses later on when you know which model to use. But the most conservative you can do is just take half of the tensile strength. So the tensile strength is 36 KSI. The shear strength that we're going to approximate is 18 KSI, which is not much. I mean, so if our tau yield, this was elastic, so this would be the yielding. 18,000 psi. Our tau max is 7,243 psi. So our factor of safety is what? Let's just drop that into MathCAD. I really don't have a calculator sitting here handy to work with. So tau y was 18,000 psi. Factor of safety equals tau y. Whoops, didn't hit tau. Y divided by tau max. So 2.5 for a factor of safety, which is usually sufficient. Okay, so that's a pretty straightforward example of how the numbers work together in a torsional shear stress setup. Let's look at web work a little bit. We've got plenty. Oh yeah, we have plenty of time. We've only gone what, 30 minutes maybe, so not long at all. That's kind of an aside, but that's kind of true for these last topics. Is they're much more condensed. I guess I could compile them all into one lecture and talk about a bunch of things at once, but these topics are a little bit shorter, simpler topics. So if you're getting kind of nervous about your final grade, just know that the third test, it does go back and include material from the first and second exams, but in general, the third test is simpler. Like the topics are things like this torsion, some pressure vessels where the equations are not much to think about. There's not a lot of difficulty in setting up a free body diagram for a frame or something like that. It's a lot more direct. So normally the third exam is the highest of the three when you take all three exams. So that's just a bit of like, don't worry too much if you're getting a little worried about your final grade, that the third test should help out on that final grade. So let's look at what this one is. Let's see, this is an optional 3, problem 1. So this one doesn't even talk about the shear stress. It's just trying to figure out what are the torques in different sections of this shaft here. So this shaft with 5 different, maybe they're pulleys or gears or something like that. I'm not too concerned in this class about if they're a pulley or a gear or just a roller of some sort. We're more interested in what's happening on the shaft itself, and we're not thinking about the shaft deflecting and bending out of shape, which it will do. We're just thinking about just the torsional shear stress. So that's one thing about this course is we've done axial stresses, we've done flexural stuff, now we're doing twisting stuff, but in this course kind of an intro course, we don't do something that stretches, flexes, and twists. So that's like the real thing. We keep them all separate, and then the next course and the courses after that, if you need those, are where you start combining all these loadings together. So try to, when you visualize these things, what is this shaft doing? Try to not think about a real shaft that might also be deflecting, flexing somehow, or maybe even pulling or compressing. You're really just thinking about it pure torsion for what we're doing here. So let's grab this picture, copy image, and let's put that in our, where'd it go? Here, yeah. So we're over here, and all I did is copy and paste. Let's write in what my different torques are. Also, just some of these torques are kind of look like they go up and some look like they go down. That is important, which ones are opposing other ones. It's not important which ones you call clockwise and which ones you call counterclockwise, or if you call them up and down or whatever, as long as you recognize that some of them are opposing other ones. So that's the main point. So for me, TA is 75. These are kip feet. So remember, a kip is kind of you took the kilo from the metric system and put it in the US customary system, and now you have 1,000 pounds. So kip feet, though, because it is a torque. B is 90. C is 40. D is 25. And E is 50. And what this problem is asking us to do, I guess we can look at that real quick. It just wants us to, what are the internal torques in each of these sections? So between point A and B, what's the internal torque there? So that's all I want you to do. So this one is a good one to start out with, because this is the fundamental part of finding out what torque you're even using in this equation right here. This is going to be the T in our torque or shear stress equation. So what you do is you go in, if you want to know what's the internal torque, and I want T between A and B. So, I'll draw a little free body diagram between A and B, and it'll look something like, I've got let's just draw it from a side view so I don't have to try and draw these cylinder things. We'll just draw a side view of them. There's the little pulley, whatever it might be, and here's the shaft. How can maybe I shouldn't try to do that. It's just because it makes it hard to line it up. And so I've cut it open. Well, there's my little cut line that I made. I'm just going to draw this torque as an up arrow, TA. And so to make this little free body diagram in equilibrium, if it's not in equilibrium, it is moving relative to the rest of the shaft, which means it's broken away from it. So to make this in equilibrium, I need TA going down. So the torque in section AB is equal to 75 kip feet. It's just going in the opposite direction. This particular problem wants me to assign positive and negative based on if the interval of the shaft is being torqued in the direction of TA. So mine is opposite of that. So, but TA, designate that torque as positive. So mine is moving opposite of that, so this must be a negative. So let's just go ahead and make sure that we've got that correct. So minus 75, and it already has the kip feet units out there, so I don't have to write that. And let's just make sure that that's what, we logged out. Let's log back in. And we were right. All right. So let's do the next one. That one was a little bit trivial, but let's do the next one. So the next one is I want to know the torque in between B and C. Oh, I wrote A, but said B. B and C. So I draw my free body diagram between B and C. And again, I'm going to draw the left-hand side, and it's going to be all of what I had for the first piece. And then I get to B. There's some kind of gear or pulley at B. Then I go a little bit further, and that's where I cut it open at. So this one has TA here. Let's put the numbers this time instead of the letters. The number is 75. I'm going to leave the units off. These are kip feet. I'm only, well, let's write the units. I don't like leaving the units off, but it does get kind of cluttery. And then at B, I've got 90. So for here, I need another 15 to make this balance out. 15 plus 75 going up equals 90 going down. And you know, is that clockwise or counterclockwise depends on which point of view you're taking on the shaft. All right, so it should be, and this one matches the direction of TA. So in web work, I should be able to put just a 15 in here and get it right. Yes. All right. Let's do the next one. This next one's probably the last one we need to do, but on this. So this one we want to know the torque between C and D. And so we would have all of that stuff we had before, A, B, C, and then we cut the shaft open between C and D. So A was 75, B was 90, the applied to C is upwards 40. And so now I need a downward torque, and I'm just using up and down to describe them because clockwise and counterclockwise may not mean, you might look at it the opposite of what I'm talking about. So normally you do talk about torques in clockwise and counterclockwise, not up and down. So what have I got? 115, and I've got 90 going down, so I need 25 more going down. We'll go over to here, plug in down, so minus 25. And we got that one right. And the last one is 50. You could get that just by looking at, well, the last section here. If I cut this and looked at only this side, there's 50 there. And so I'd have to have 50 inside there. Getting the right direction on that might be a little challenging because if I look at this circled free body diagram, that's the opposite side of what I have been looking at. So you have to be careful with the right direction on it, the positive or negative. All right, so that's not really talking too much about the shear stress. It's just setting you up to be able to calculate a shear stress. So let's go to another problem, see what the next one is. Okay, that one's similar, but it does have you calculate shear stress, but it's too similar. So let's look at another one. This one doesn't have a picture. This one does have that angle of twist, which we haven't talked about yet, but this one is also basically what we just did. It just not just did, but just as our first example, it's not much different than that. So I don't think that's a good one to do. Let's see if there's something else. Oh, this might be good. Let's see. Both shafts. I don't know what they're. Okay. Oh, okay. A, B, and B, C. They look like one solid shaft, but they're actually apparently two separate shafts. Again, that's kind of the same problem that we've been doing. I wanted something that had a little bit. Oh, okay, here's something different. All right, let's do this one. Let's get this picture. Where's copy? Oh, you can't look at the picture. I'll show you in a second. Here's the one I'm looking at. Well, that's the one I'm looking at right there. This problem. The other, I went through. This is optional 3, problem 5. So the others that I looked at were just basically the stuff we'd already done. So this is the shaft is an annealed ENGR hollow tube. That's the one that's attached to the wall back here. So you can kind of see that dotted line is showing that it's hollow. And it is securely connected to an extruded magnesium rod BC. So that's this other piece in the front part, and it's solid. Tube AB has an outside diameter and an inside diameter. Rod BC has an outside diameter. We've got 2 torques. We got some links. Determine the shear stress in both sections of the shaft, and then angle of twist, which we're not doing angle of twist today. So let's take this problem and work on it, I think. I'm not sure what's going to happen if I try to paste this. It worked all right. All right. So let's go back over here. So here's our little problem. The text is kind of small, but oh, well, it's covered up with that. Let's scroll where you can read it. All right. So let's label some stuff on here. L1, it's weird. It's I guess that's just a function of how I copied. L1 is 1.8 feet. L2 is 3.2 feet. T1 is 110 inch kips, or kip inches, and T2 is 45 going the opposite direction. Okay, and then we've got these 2 different materials, ENGR and what was our other one? Magnesium. Okay, so the materials, unless we were doing the factor of safety, the materials don't actually mean anything for what we're doing here. What they mean for this problem is this problem also asks us for an angle of twist, which does depend on a material like the modulus of elasticity, except it's the modulus of rigidity, which is the same idea as modulus of elasticity, except applied to torsion. All right, so this one's not too much difficult from what we've been doing, but let's work on it. And that's the thing about these is they're pretty straightforward. They're not too confusing. Let's do this guy. So I'm going to chop off the little end close to T2. I'm going to draw the side view. I'm not going to try to draw it in 3D. So here's the side view of that picture. I'm going to say that this torque is going up from my side view point of view. So the internal torque there must be going down, and it must be 45 kip inches. My equation, tau in BC, equals the torque in section BC times the outer radius of section BC, if I want the maximum, which I'm pretty sure it is asking me for maximum. Let's see if I see something. Well, it really doesn't specify maximum, but that's what it means. It wants the maximum. Over J for section BC. Well, I got kind of jaggy. So let's put in the stuff we know. The torque in there is 45,000 inch-pounds. So I'm putting in the 45,000 for the kip. I guess if I left it in kip instead of pounds, then my answer would come out in KSI, which would be fine. C is, let's see, oh, where are my dimensions for this? So tube AB, rod BC has a diameter, so outer diameter, of 3.4 inches. So that means the outer radius is just half of that. So 3.4 inches over 2 will be the value for C. And then polar moment of inertia is pi over 2 times the outer radius raised to the 4th power. So 3.4 inches over 2 raised to the 4th. Right? It's got to be, well, let's just open up MathCAD. There it is. And let's try to put this equation in there. I've already forgotten it. T is now equal to 45,000 inch-pounds. Oh, I erased my 45,000 somehow. There we go. C was OD over 2, where the OD is 3.4 inches. And then J is pi over 2 times C to the 4th. And then we should be able to calculate tau for, this is just for section BC. T, which equals T for section BC times C for that same section over J for that section. So 5.831 KSI. Let's see if we're right. 5.831 over here. Correct. All right. AB, this one's slightly more complicated, but it's not that bad, but let's do it. So, let's look at our picture though. Here we go. So for AB, I need to draw the free body diagram between point A and B, and it might look simpler to draw the left-hand side, and it might be. There is one thing about that, the left-hand side is attached to the wall, so you're creating a free body diagram, which means it can't be attached to the wall. So that means you have to replace the wall with whatever force the wall is applying to this shaft. And the force it's applying would be the 110 minus 45, it would apply the balance of that. So you could do that. I'm just going to draw the free body diagram from the free end over to AB, which will give us the same thing. So here's what I want to do. Here's that section. And then here is our magnesium section. I've got 45 kip inches here. And I've got, what was it, 110? Oh, yeah, 110 going down though. And so I need more going up, right, to balance this out. So the internal torque between A and B equals 110 minus 45, so that's 65, right? Now, I don't know if they're going to want a positive or negative stress here. Normally shear stress doesn't matter if it's positive or negative because it's the difference in, failing this way or failing this way, and it's no real difference. So it probably doesn't care if it's a positive or negative shear stress. Oh, I never wrote down our answer for that. What was it? Where'd it go? 5831. All right, so let's do our tau for AB. It equals the torque in AB, which is 65,000 inch-pounds, times the outer radius, which I didn't write that down. Let's see. Outer diameter is, tube AB has an outside diameter of 4.95 inches. And then it has an inner one of 2.45 inches. Okay, so let's use those numbers. So the outer for C, because we're assuming this problem wants us to calculate the maximum, wait on that, would be the 4.95 over 2. So that's TC. This J is going to be the one that has C and B in it because it's a hollow tube. So pi over 2, C to the fourth, which is 4.95 over 2, minus the inner one, which was, what was it, 3.4? No, 2.45. 3.4 was the outer other one. So 2.45. Raised to the fourth. All right. And that's going to equal something. We'll plug it into MathCAD and find out. Let's see. All right, we've got a new value for torque was 65,000 inch-pounds. We've got C is 4.95 over 2. We've got B was 2.45. Let's see, that's TC. That'll give us J. That's all we need, isn't it? All right, so tau for section AB is this new version for T times new value of C, TC, over J is pi over 2 time, well, let's put times in there, times C to the fourth minus B to the fourth. And put in KSI. 2.904. So let's see if our web work likes that number. And it does. There we go. So that's kind of the idea for torsional shear stress. Next time we'll add in the idea of angle of twist, maybe work some more torsional shear stress problems and angle of twist together, kind of just for some more practice. So it shouldn't be a very long topic for tomorrow. And then we'll do some power transmission. And that's it for torsion. Then we'll move into pressure vessels and some stress concentration factors. Remember, though, the other thing that's going on in the background that, unless you ask particular questions about it, I won't say a whole lot, is the truss project. So don't forget that you need to get your team, 3 people is ideal, and do the truss project. Don't forget that that is still going on kind of in the background. And if you have questions about that, also, then let me know and I'll try to answer them the best I can. There is one topic on the truss that I need to mention, and that's about buckling. And so we'll do a day or a piece of a day talking about column buckling. All right, so sorry this one didn't stream the way it should, but I'll upload this. It should be ready in a little bit. Obviously, if you're watching that, it's already ready, but I'll see you tomorrow one way or the other.